We are
Good
live.
evening. Welcome to all of you, all who are present in the Zoom and YouTube for this special Bibha Chowdhury Memorial Lecture, which is part of Vigyan Vidushi 2022 Physics. I am Vandana Nanal, one of the conveners of Vigyan Vidushi Physics. The special lecture, we are very fortunate today to have one of our illustrious alumnus of TIFR, Professor Sarbani Basu, astrophysicist, to give this lecture. And before I request Professor Poonam Chandra to introduce her, I'll take a minute to introduce and remind us, some of you, about Bibha Chowdhury. Let me share my screen. So some of you would have heard about Bibha Chowdhury in the last couple of years, but to a great regret, for many years or many decades, she remained hidden. And though she has done a very pioneering work in around 1930 and 40. So who was Bibha Chowdhury? She was the first woman particle physicist of India and an experimentalist too. She did her MSc from University of Calcutta in 1936, and as you can imagine, almost 8 decades back, she was the only
Here's
woman
what I found online.
Between 1938 to 1944, she worked with D.M. Bose at Bose Institute on the development of the technique which allowed them to determine the moment of charged particles by observation of tracks in photographic emulsion plate. They worked with the quality of the plates available to them, and that was the limitation in what they could do, because actually the technique which they suggested and developed was made quite a big breakthrough in the field. In 1945, she moved to UK to do her PhD, and she did her PhD under the supervision of PMS Blackett, who won the Nobel Prize in 1948 at the University of Manchester. After completing PhD, she came to TIFR to become the first woman scientist at TIFR. She built the bubble chamber and set up the detectors for air shower studies. Thereafter, she moved at both abroad and at different places in India, and finally settled down in PRL around 1961 to 1976. She worked there on various cosmic ray air shower experiments at Kodaikanal Observatory and later at Kolar Goldfield Mine. Again, she was the first woman scientist at Physical Research Laboratory, Ahmedabad. After her retirement in 1976, she went back to Kolkata, and till her last breath, till 91, she worked in Kolkata on understanding nucleus-nucleus interaction at relativistic energies to obtain information regarding astrophysical and cosmic ray phenomena. She also carried out experiments at VECC. And I really feel bad at a personal level that I actually missed a chance of meeting her then. What is to be noted in her achievements is that if you look back at her work from 1938 to 42, working with D.M. Bose, she actually did publish 4 Nature papers. That is, the papers, research papers in a very, very prestigious journals, giving the significance of their work. And this work was about identifying a cosmic particle having mass close to 200 times that of electron. As I mentioned, the more accurate measurement was done later. This technique developed by them actually paved the way for the discovery of pi meson, which was later done by Professor Powell, and he got a Nobel Prize for that in 1950. Not then, but a decade later, Professor Powell acknowledged Bose and Chowdhury's pioneering contribution, which paved the way for this pi meson discovery. In words of the historians S.C. Roy and Rajinder Singh, they describe Bibha Chowdhury very nicely, saying that she belongs to the first generation of women scientists who began their research career in pre-independent India. Born more than 100 years ago, opting for a research career in physics, visiting England for further research, and working in 2 premier research institutes after her return to India were no small feats to accomplish. Unfortunately, she somehow remained away from the limelight and was forgotten with time. So if you look at her work, she did experiments at high altitudes in Darjeeling, in India, and in Alps, in deep mines, coal gold fields, under very, very challenging conditions. If you ever have a chance to visit any of these places or the laboratories at these places, you will realize difficulties even today, and you can imagine what problem she must have faced in 6-7 decades ago. As I just said, unfortunately, no accolades came her way during her lifetime, but she was completely unfazed by all the inattention and immersed in pursuit of science. Thankfully, a book which was brought out in 2018 by Roy and Rajinder Singh, titled A Jewel Unearthed, Bibha Chowdhuri. This brought her work in limelight, and the Indian edition of this book has been published by TIFR and the TIFR Alumni Association. 2 posthumous honors have been bestowed on her recently. In 2018, the International Astronomical Union named a yellow white dwarf star as Bibha, and in 2020, the Government of India declared a chair professorship in her name to be instituted in TIFR or PRL. The Indian Physics Association also brought out a special issue of their quarterly bulletin in her memory, which is available on the website. I will put these links later also on the Moodle and in the chat box. So this memorial lecture started last year as a part of Vigyan Vidushi program. So this is the second Bibha Chowdhuri Memorial Lecture, is a token tribute to her. Her life story is exemplary and inspirational to younger generations. So we hope all of you would really take inspiration from her story. Thank you. And I now request Professor Poonam Chandra to introduce today's speaker for Bibha Chowdhuri Memorial Lecture.
Thank you, Vanna. Good afternoon, everyone. It is my pleasure to introduce today's speaker, Professor Sarbani Basu. Professor Basu is the William K. Landman Junior Professor of Astronomy at Yale University in the United States. Professor Basu is our own alumni. She joined TIFR, University of Pune, for the master's program in 1986. And later she joined Department of Astronomy and Astrophysics of TIFR for her PhD work, which she completed in 1993. And then she held postdoc positions in London, Denmark, and finally at Institute of Advanced Study in Princeton. She joined Yale University as a faculty in 2000. And since then, she has won several awards and accolades. She received the Enu Bapu Gold Medal of Astronomical Society of India, which is a very coveted award, in 1996 for her early work in helioseismology. She was also awarded the United States National Science Foundation NSF's Career Award in 2004. In 2018, she was awarded the George Ellery Hale Award for the Solar Physics Division of the American Astronomical Society. She is an elected fellow of the American Association for the Advancement of Science and the American Astronomical Society. Professor Sarbani Basu conducts research in the fields of solar and stellar astrophysics using seismic data. She has been studying general properties and the details of the structure and dynamics of the sun. And one of the important points I want to focus here is that Professor Basu believes very strongly in the inclusion and equity in science, and her work begins at school level. And to this end, she works with the school teachers from under-resourced regions, and she helps maintain their students, especially their female students' interest in science. I'm sure Professor Basu will herself tell you the fond memories of TIFR days, but she does remember those pre-internet days where she could sit late night in the canteen, sip tea, and discuss science rather than spending time on the phone, which most of the students do now. She was also, bothered by the fact that there were not enough women scientists at TIFR. And she's hoping that the things are better now, and we all hope so for that. And having said that, I would again like to thank Professor Basu for agreeing to give the lecture, and floor is all yours.
Thank you, Professors Nanal and Chandra. I would like to begin by saying that it is an immense honor to be giving the Bibha Chowdhuri Memorial Lecture. As Professor Chandra indicated, when I was a student at DIFR, there were very few women, particularly in faculty positions in the physics group. And I hope that has changed, though how much it has changed, I don't know. The one thing I would urge all the students who are attending this program is don't let the lack of role models stymie you. You need to become the role model if you don't find any. Just look for mentors among whoever is there. And remember, one mentor is not enough. Look for multiple mentors, because every person has, their own point of view, are stronger, would be strong advisors in one aspect of your career, if not the other. So look at multiple people and advocate for yourself. Don't listen to people who would say that you can't do this, you can't do that because you happen to be a woman. Just don't listen to them, because you shouldn't let others sidetrack you from your dream. It is your dream that you're pursuing. Don't let others control it. You should do everything that you can. So having said that, I would like to share my screen and talk a bit about my research. It's not just my research, because of course, it's a field where others have worked before, and there's a huge group of people still working on it. And that's about the star. And I call this living with a star for a number of reasons. I mean, one is the obvious one. We live in the backyard of the sun. It's a star. It's often a trick question I ask my undergrad students, what's the closest star? And most of them will say Proxima Centauri. No, the closest star is the sun. And I would really like to dedicate this talk to not just Bibha Chowdhuri, but all other unsung heroines in science. Women have always had to take a back seat, and I think it's time for us to change that. I mean, there's this infamous story of Nobel laureate Lisa Meitner, and by backseat, I'm not just talking about India. I mean, there's the story about Lisa Meitner, who won a Nobel Prize. She wasn't allowed to use the front doors to enter her university. She had to go through the back doors. So don't let that happen to you. And as I said, advocate for yourself. Okay. So the sun is our nearest star, and it's pretty obvious why we bother studying about the sun. And it affects everything on Earth. It's responsible for life on Earth. Without solar energy, we won't be here. And one way or another, even today, we use solar energy, whether it's fossil fuels or, solar panels or food, it's all solar energy. So yes, so we need to understand that properly. We need to understand the sun. But sun just doesn't give life. It can have harmful effects. Particularly, the sun has a magnetic cycle, and that magnetic cycle can cause geomagnetic storms, which can cause, and solar flares, which can actually harm technology and cause a lot of damage. So life today is quite vulnerable to these solar storms. And by short time scales, I really mean time scales on human lifetime scale. So this image shows the evolution of the sun, or the changes at the surface of the sun. It's fairly high above the surface. It's what we call the corona, which is a very hot layer. From 1996 to 2020, and you can see that in X-rays, the sun is brightening, dimming, brightening again, dimming again, and right now it's again brightening. This is what we call the solar cycle, this brightening and dimming. And this is what is an issue for technology. Now, the surface of the sun shows dark spots. And this is an example. And to scale, I don't know if you can see it right here, is drawn to scale the Earth. So these are humongous dark spots. These numbers are just numbers that are given to identify the spots. So these are called active regions because they're magnetically active. So this is active region 1476. If you zoom into a dark spot, it's actually very pretty. This is an image from the Daniel K. Inouye Solar Telescope, the most high-resolution image of a sunspot ever seen. Each of these sort of, bright spots here are a few thousand kilometers across, and this looks like a sunflower. And these are regions of immense magnetic fields, and this is what we are trying to figure out what's going on. Now, the dark spots are dark only when you look at them in visible light. So this is what we were looking at earlier. But if you look at the sun simultaneously in different wavelengths, you see that in some wavelengths, the spot is actually not dark, but bright. That's why we prefer to call them active regions instead of just sunspots. Sunspots is a historical term because people used to look only in optical light when it looked dark. But if you had X-ray eyes, these would be very bright regions. Okay. Now, the number of sunspots increase and decrease in a quasi-periodic manner. So this is a record of the sunspots. The good record starts where the graph is plotted in blue. And you can see the numbers increase and decrease and increase and decrease with a period of roughly 11 years. And I call it quasi-periodic because that's exactly what it is. Some of the cycles are 9 years, some 11, some 14, but roughly speaking, 11 years. And the amplitudes of the cycles don't remain the same either. And some of these regions emit huge amounts of energy and particles. And I'd like to show you a movie showing what's known as a coronal mass ejection. This is an immense amount of material that is ejected and which can, if it comes towards the Earth, can cause problems. Now, the image you're seeing, it's the actual sun has been eclipsed artificially because the light here is much less, it's not as bright as the surface of the sun. So in order to see it, you have to produce an artificial eclipse. So this white ring is the actual size of the sun, but you're covering an area which has a radius twice that of the sun. Only then can you see these features. Now this speckle is because of all the particles hitting the detector. So the SOHO spacecraft is at the L1 Lagrange point between the Earth and the sun. That's the point between the Earth and the sun where the gravitational forces of the two bodies cancel each other out. So it's about 3 times as far away from the Earth as the moon is. So these mass ejections become more and more frequent as the number of sunspots increase. And these can harm us. So this is what happens. You get an emission from the sun, it interacts with the Earth's magnetic field and causes a disturbance, which is basically what a geomagnetic storm is. The particles also go towards the poles and form aurora. Now, the first indication that these phenomena can affect society was the so-called Carrington Event of 1859, when Carrington, who is a British astronomer, saw a gigantic flare. It was a white light flare, so he could see it. And what was reported that telegraph operators found sparks leaping from their equipment, some bad enough to set fires. That's because these particles overloaded telegraph wires. Remember 1859, there were no electric lines. The only lines around were telegraph. And that was the height of technology at that time. Okay. And ice core samples have since shown that the Carrington event was twice as big as any other solar storm in the last 500 years. If we had such a Carrington event today, it would cause huge disruptions because it would affect satellites. So GPS, your cell phone, if you use a credit card, everything could be affected. And of course, which means it would cost billions and billions of dollars to repair. So one of the reasons people are trying their hardest to figure out if these events can be forecast. And the ultimate societal impact, it almost caused a nuclear war in May 1967. So a solar storm basically caused radars, American radars based in Greenland and Northern Europe, to malfunction. And they thought they were being jammed by the Soviets. Fortunately, by then, the US Air Force had solar physicists working and trying to figure out what the sun does. And even though Air Force aircraft were on standby and had the engines running, everything, they were called back right in time. Okay, so what is the problem? I mean, we are the first quarter of the 21st century. We'd think that we'd have handled this by now. The problem is we still don't know enough to predict the events, and for that matter, I mean, forget about predicting each individual event. We can't even predict the trend of the solar cycle. So you saw the ups and downs in the solar cycle curve that I had shown. We can't yet determine whether a solar cycle will be high or low, because the higher the solar cycle, it means the more sunspots, the more the chances of such huge storms. And this is a sorry tale of our inability to predict. So solar cycle 24 was the solar cycle that lasted from about 2010 to 2020. So the last solar cycle. We are in solar cycle 25 now. The strength are predictions of the strength of the solar cycle. The dashed line here was the mean of the last, I forget, I think 5 or 10 solar cycles. The dot dashed line here is the sort of mean of the predictions shown as the color bars. Turned out this blue line is what we actually got as the strength of that solar cycle. So we're waiting to see what the current solar cycle will say. So these are the predictions. You can see that fewer people decided to predict, given how they fared the last time. This was the average of the previous cycles for which we had data. This was cycle 24, the one we failed so badly to meet. And we'll know in about 2 or 3 years which of these predictions is correct. So what can we do? Well, we want to detect and hopefully understand what's happening inside the sun, because ultimately it's the processes that happen inside the sun that manifest on the surface. Okay, so what do? We first model the sun. Now, this is where you're physics students, so this is where physics comes in, and it's actually fairly simple. All we have to do is model some conservation equations. So for most of the parts, stars and the sun are spherically symmetric. So the internal structure is only a function of radius, which means we don't have to bother about the 3D nature. We have a set of 1D equations. 1D is easier than 3D to solve. So what do we solve? The conservation of mass, conservation of momentum, thermal equilibrium, conservation of momentum, because otherwise, of course, parts of the sun would move, thermal equilibrium, because if thermal equilibrium didn't happen, the sun would either puff up or, contract. We have to figure out how to transport energy, whether it's convection or radiation, which needs opacities, which tell you how opaque the material is. Stars shine through nuclear reactions, so we need nuclear reaction rates. We need to figure out how abundances change, because after all, reactions, the reason the sun shines is hydrogen is being converted to helium. So the abundances keep changing. And we need the equation of state. That's the relation between pressure, density, temperature, and abundance. Now, gases are easy, so the equation of state is not that hard. So this is a schematic cutoff of the structure of the sun. It's quite simple, actually. You have an energy generating core, which produces energy, and energy is transported through radiation, meaning matter doesn't move, to about 30%. So the inner 70% here is the radiative zone. The outer 30% is a convection zone, meaning heat is transported through bubbles of gas rising and falling. So think of it as boiling, churning matter. Do we know that is correct? Yes, the surface of the sun shows that. These are convection cells at the surface. The white parts are upflows, the deep parts are downflows. In fact, you can see it as a movie. This movie never runs very well, so I'm sorry about that. This is a movie from the National Solar Observatory where they show how the granulations, it's a dynamic process. These bright spots, incidentally, are small magnetic fields. Now, the thing is, our usual solar models, they do not model short timescale variations. These models evolve on timescales of millions to billions of years. And we don't really know how to invoke magnetic fields in them, so they don't really mimic the solar cycle either. So they satisfy the global constraints, so we know the models have the correct mass, the radius, surface temperature, total energy output, but we cannot be certain that the internal structure of the sun is correctly reproduced. And for that, to test our models, we need seismic data. So we do seismic studies to probe the internal structure and dynamics of the sun. So that is what we call helioseismology. It's the study of the sun using solar oscillations. Now, it's quite different from what seismologists do for the Earth. In the Earth, what happens, there is a disturbance, an earthquake. The disturbance travels to different ground stations. You note the difference in time between the earthquake here and what the different ground stations do, and then model that. On the sun, we use normal modes, okay? Normal modes are what happens if you disturb a body in equilibrium. It'll pulsate till it settles down. Now, we are used to normal modes in physics, so we're used to normal modes in spring. It's a 1D system. You have the fundamental mode where you have nodes at the two ends. You have the first harmonic where you have 3 nodes, 2 ends and 1 in the middle. You have the second harmonic and so on. So just one number is enough to describe these oscillations. How many nodes are there? 0 nodes in the middle, 1, 2. In the case of a drum, the surface of a drum, it's a 2-dimensional body. So you could have nodes along the perimeter or along any radius, but you could also have nodes in the, along a circle, but you could have nodes along a radius. So you need 2 numbers to describe it, the number of nodes along a circle and the number of nodes along the radius. So 0 along the radius, 1 along the circle here. These, incidentally, you can describe these by Bessel functions. But in the case of a star, we have 3 dimensions. So you have dimensions 2 dimensions on the surface, so latitude and longitude, theta and phi, and also inside along the radius. So we need 3 numbers. And what we do, and for those of you who've already had quantum mechanics classes and have learned how to do the wave function of a hydrogen atom, the surface we describe by YLM, spherical harmonics. The inner part, unfortunately, it's not something as simple as the Legge polynomial in quantum mechanics, the hydrogen wave function, but it can be calculated. So let's see, let's give you a crash course in helioseismology. Now, the sun oscillates in millions of different modes, and the oscillations die out but are re-excited all by this outer churning layer. The oscillations are linear, meaning they have small amplitudes, and adiabatic, meaning fast enough that they don't exchange heat. The linearity is a good approximation, adiabaticity not so good, but it's a workable approximation. All modes that we've observed are sound waves, meaning acoustic modes, which we call P modes, P per pressure, or surface modes called F modes, okay? And each mode, remember, we are in 3 dimensions, is characterized by 3 numbers. N, the radial order, which is the number of nodes in the interior, and then L of the YLM, which is the number of nodes on the circumference, and M, the azimuthal order, which is the number of nodes on the equator. Now, if the sun were spherically symmetric and did not rotate, all modes with the same L and N, but different M's would have the same frequency. Again, think hydrogen atom. An unperturbed hydrogen atom has degenerate energy levels. In this case, we have degenerate frequencies. We lift the degeneracy by giving it rotation when the modes split into 2L plus 1 different frequencies. Again, hydrogen atom, Zeeman effect, put in a magnetic field, you will split the modes. Now, given that we observe very high L modes in the sun, we don't try to find the frequencies of every mode. We find the frequency of a central mode and define the rest as a polynomial in M. And the nice thing about this decomposition is this quantity is determined by structure, and the odd order coefficients are determined by rotation. So we can separate things out nicely. Different modes penetrate to different depths, and that allows us to build up a picture of the sun. Now, you could easily ask, how can we observe sound across empty space? Well, we don't. We observe the disturbance caused by the waves on the stellar surface. So this, for example, is a movie of oscillations. We removed the signature of rotation and of that churning granulation, and this is what you see on the sun. Now, we have enough data that instead of, doing what's normally done in astrophysics, where you make a model, calculate its observables, and then compare the observables. If the observables agree, you say you have a good model. We actually take these sun's frequencies and try to figure out directly what the structure of the sun is. We don't depend on models to try and find out the structure of the sun, except indirectly. So this equation, horrible looking it may be, it's actually quite simple, is the relationship between the frequency with which one mode of the frequency of the sun, the displacement eigenfunction, because frequencies are eigenvalues, the density, the sound speed, pressure, but pressure, because it's a star in equilibrium, depends only on density, the acceleration, and the acceleration due to gravity, which also depends on density. Okay. So the frequencies are just a function of sound speed and density. The problem is we can determine what the frequencies are through observations, We want to find the density and the sound speed, but we have no handle on the eigenfunction. This is where, again, methods of quantum mechanics comes in. Chandrasekhar, the same Chandrasekhar of the Chandrasekhar limit white dwarfs, showed in 1964 that this equation constitutes a Hermitian eigenvalue problem, just like the problems we have in quantum mechanics. So you can use variational principle to linearize this equation around a known model and look for differences in the frequencies, or rather differences in the structure. So this is the linearized model. We know this quantity. This is the difference in frequency between the sun and the model. We want to find the difference in the squared sound speed between the sun and the model, and the difference in density between the sound and the model. These two quantities, the k's, are known as the kernels and are known functions of the model. So we can solve this equation, and what do we get? But before that, what do the data look like? This is a set of data, one of the many sets of solar frequencies that we use. On the x-axis is the degree L, on the y-axis is the frequency. This is the surface mode, and these are the various tones and overtones. The reason we can use this data well is this. What I'm showing here are 5,000 sigma error bars. In astrophysics, other than pulsar timing, there are very few measurements that are this precise. Okay. And yes, our tests have shown we can actually invert for the structural difference. If we take two models and try to invert for their structure, we can do so. So what this graph shows, the solid lines are the actual differences between the two models, and the dots are what we get if we invert their frequencies. So we know we can do it. And this is what we see for the sun. These are two separate models, I call the red and the blue, slightly different internal physics. I would like you to concentrate here. This is the sound speed difference. Look at the axis. This is a 0.5% difference, meaning the models are darned good. Yes, they're not perfect because you can see this is a many sigma difference. For most fields of astrophysics, we would say, yeah, we have a perfect model. But with the precision of the data we have, we know there are some problems, but these are not major problems, because if there were major problems, we'd have much larger differences. We think we know what this is caused by. Our models are static and don't include the effect of rotation on structure. And if you do that, you can get rid of these structures. So our models are very good. The problem we have is not for structure, understanding the structure of the sun, but understanding internal rotation. Before we had helioseismology, this is what we expected internal rotation of the sun to look like. If you took a section of the sun, this is the axis, that's the equator. The isorotation contours of constant rotation were expected to be parallel to the rotation axis. In other words, the sun would be rotating as though different cylinders that constitute the interior of the sun were rotating at a different rate. However, even the first helioseismic results that came out in 1985 showed that is not so. This is a more updated result for solar rotation. Look at the contours here. They look nothing like parallel to the rotation axis. If anything, there's the differential rotation on the surface. So we've known for a long time that the equator of the sun, at the surface at least, rotates much faster than the poles. But what helioseismology has revealed that this continues up to roughly where convection in the outer layers give way to radiation in the inner layers. This layer we call the tachocline. And in the interior, we have almost solid body-like rotation. These spaces are where we don't have sensitivity. So this is a bit more detailed. So I've taken latitudinal cuts of the rotation rate and produced them in a usual two-dimensional graph. So you can see there's the surface rotation. Rotation increases slightly inwards. It's almost constant, then it changes suddenly. So these regions where rotation changes suddenly are, of course, regions of shear. There are two main regions. One we call the tachocline. Tachocline just means a region of changing velocities, and one we call the near surface shear there. Now, that's not the only thing. If you look carefully, there are things called zonal flows. Now, this is just an image of jet streams on Earth. Jet streams are these streams of wind, you know, some going east, some going west. These are also seen in Jupiter. Some layers are prograde going in the direction of rotation. In this case, the red layers, and some going away from the direction of rotation. Okay. And we have flows on the sun that go from the equator to the poles. And additionally, if you look close to the poles, we can't look at the poles. There are these swirly features, which we have no idea what they are. They're probably related to, when we found this in 2015, we really didn't know what they are. Though they are probably related to the recent discovery of inertial modes on the sun. So there are all these dynamic features of the sun, and the one thing we really don't know is what causes them. So what we can see are these solar cycle related changes inside the sun. All the dynamics that I showed you, every feature changes with solar cycle. So we had known for a long time that solar frequencies change with activity. When there are more sunspots on the sun, in other words, high magnetic activity, the solar frequencies are higher than when there are fewer sunspots on the sun. We still quite don't know why that is, but that's the thing. It's not just the frequencies that are different, but the frequency splittings due to rotation, those are different too, which allows us to, to find differences in rotation rate. So what this plot shows is the difference in rotation rate between two solar cycles, cycle 23, which lasted from 1996 to about 2000. And no, I beg your pardon, 1996 to 2009. And cycle 24, which started just after 2009 and lasted till 2020. And you can see that, and by the way, so that color scale gives you the rotation rate in meters per second. The errors are 5 to 10% on this number, okay? So we have significant changes in the rotation rate of the sun. Now, if we look at the zonal flows, remember we talked about east-west flows, those change. Now, it's very difficult to denote the changes on a graph like the one you see here. So what we do is at any given epoch, we take the longitudinally averaged zonal flow, and we plot it as a function of time and of latitude. The way you do it, you find the velocity and subtract the average velocity, and you get the changes. Now, the top and bottom panel are showing the sun, but two different missions. What you can see, I'll concentrate on the bottom panel, is there are these prograde flows, which at the beginning of the solar cycle start at the mid latitudes, then by the time you hit solar maximum, given by this line here, reach the equator. And at the same time, the flows from the mid-latitude that go up to the poles. And the interesting thing is this equator word flow, that is where it appears that sunspots appear. So this part between one side of this white line is solar cycle 23, other side is solar cycle 24. We only have about 2 solar cycles of detailed helioseismic data, but at least the position of the sunspots always tend to be on this flow. Now, why this happens, we don't know. We don't know if it's the sunspots that's causing the flows to change or the flows that are causing sunspots to appear there. So it's the classic chicken and egg problem. Probably much more complicated with the feedback, but we do not completely understand this. And the other thing you will see from this figure is that the flows in cycle 23, which was a stronger cycle, were much stronger than flows in cycle 24. Remember, these are the interior flows. Now, because this is a graph of latitude versus time, I could only show this to you at one depth. I can plot this as a function of depth versus time at different latitudes, and this is what we see. So this is 15 degrees, 60 degrees, and 2 others in the middle. And look at this flow here. At the solar minimum, here, this flow starts deep inside the sun and reaches the surface around solar maximum. In other words, the maximum of the solar cycle, in some sense, the next solar cycle has, we should be able to predict the flows at the maximum if we know what the flows are at the minimum. Again, it's only 2 solar cycles of data, unfortunately, but we'll know soon enough if this is true, even for this current solar cycle, which is cycle 25. Now, another question is, are there changes in the tachocline? Now, there was a time, not too long ago, by that I mean even 10 years ago, slightly more perhaps, when it was believed that the entire solar cycle is caused by changing magnetic fields here. That view has changed. The reason for this view was it was believed that you can't magnify magnetic fields in a convection zone. Magnetic fields are buoyant, so they'll move up and dissipate. Numerical simulations seem to show that you can actually generate magnetic fields in a convection zone too. And we have evidence from other stars that are fully convective also have magnetic fields being generated and dissipate. Strong magnetic fields being generated. However, it still remains a very intriguing area. So is there a change there? So this is just a schematic of what we show here. And what we want to know if this jump changes, because that's the most easily detectable feature of this region. What is the change in velocity, in rotation rate between the convection zone and the deep interior? Okay, turns out it changes with time. So this, it's slightly complicated graph because it has 2 things plotted. In gray, you have the number of sunspots. So you have cycle minimum, maximum, the next minimum. In red, I plot the jump. Positive jump means the outer regions have a higher rotation rate than the inner regions. Negative jump means the outer regions have a lower rotation rate than the inner regions. And you can see that it changes. But what you can see is that it's not completely correlated with the solar cycle. So the question is, does this follow a solar cycle? Or does this follow what's the sun's magnetic cycle or the Hale cycle? So in the solar cycle, you see the number of sunspots increase and decrease. At the maximum of the solar cycle, the sun's polarity reverses. So every 11, so So at the maximum, you have north and south. The next maximum, it'll be south and north. So you need 2 cycles to complete a magnetic cycle. So again, a few years and we'll know the answer. Is it really that, or is it that the changes in the tachocline are sort of non-linearly related to what's going on? We don't know. And the changes, then the difference between the 2 cycles isn't just that the time variation is different. If we plot them against the proxy of the magnetic field, they form 2 completely different hysteresis loops. So the red and brown, so the red is increasing activity in cycle 23, which is between 1996 and 2000, and the brown is decreasing, while between and cycle 24, it's the blue and the purple, and you can see at the same level of solar activity, they are different. So another mystery, why? You really don't know. So where does this leave us? So we now have more than 2 solar cycles worth of data that show us what goes on inside the sun. However, we have more observations than we have explanations. The observations have not yet been tied together in a coherent picture. There have been improvement in models, there have been improvement in simulations, but we cannot yet tie together. There are some technical challenges because simulations and our computers are fast, but however, not fast enough. We also do not understand what causes cycle-to-cycle differences. And while solar structure is actually explained to almost completely with our current theories of solar structure and evolution, stellar structure and evolution, dynamics is a challenge. Solar internal rotation is still difficult to reproduce. The near surface shear layer, which was this shear layer very close to the surface, cannot be reproduced at all latitudes. The tachocline is a complete mystery. So the question is, what do we need? More observations, better analysis. We definitely need fresher and better brains, that's for certain. So perhaps some of you would be interested in this field. So I'd like to leave you with a few thoughts. The sun is our nearest star. We depend on it for everything, but we do not understand it well enough. The reasons behind the solar cycle and associated changes are not well understood. And as I said, we need more brains, fresher brains. And while the structure of the solar interior is reproduced well by the equations governing solar structure and evolution, why the interior of the sun rotates the way it does, why the rotation changes the way it does, why do the flow change the way they do, we really do not understand at all. So I'd like to leave you with those mysteries, and thank you very much for your attention. I'll be happy to answer questions.
All right, thanks, Professor Basu, for such an interesting and informative lecture. And there are some questions on the Zoom link, so I would ask those questions. The first question is from Arpita, and she's asking that if a powerful geomagnetic storm happens against just like Carrington Event, then what steps should be taken to reduce damages here as much as possible? Or is it even possible to even try to take these steps?
That is a very important question, and there are a lot of people, particularly in the power industry, working on it. We are lucky that the SOHO spacecraft is where it is, because it will get some advanced notice that there's going to be a geomagnetic storm. And the reason for that is SOHO sends us measurements with electromagnetic waves, while, of course, what causes us damage are the particles. So particles travel with speeds much lower than electromagnetic waves. So we have time to take a few mitigation steps. One of them is perhaps a controlled shutdown of some of the power stations and substations. Because in 1989, there was a huge blackout in northern Canada because of one of these geomagnetic storms. Of course, we didn't have any means of advance notice at that point. The other thing is shield satellites. So there was a geomagnetic storm in 2003, if I remember correctly, where we did get an advance notice, and most satellites could take evasive action, in the sense shut down the critical electronics, turn the antennas around, except one, which was fried, which I believe was a Japanese television satellite. But these are steps, not so much individual as systemic steps, because it's the power system grid that needs to do it, the communications people who need to do it. For people like you and me, it's just normal emergency preparation, keeping water in hand, batteries in hand, stuff like that. But there is a lot of effort being spent on mitigation and understanding what the best mitigation efforts would be. Now, in a pre-technological era, this wouldn't matter at all. So aircraft, commercial airlines already actually take mitigation efforts whenever there's a big solar storm, since most of the particles come to the Earth at the poles. Let me see if I can find that visual. I know I have one. Sorry, this is an inefficient way to get to that. Let me try to be a bit more efficient. This one. So notice most of the effects are going to be at the pole. Now, the stronger the event, the effects go to lower latitudes. So aircraft have polar routes these days. So if there's a solar storm, both crew and passengers would be in danger because of radiation levels. So aircraft routinely take mitigation efforts by changing the routes of airplanes. So things can be done. There's still no well-defined programs or plans to do it. It's still a bit hit and miss. So, yeah.
Thanks, Professor Basu. And before I ask the second question, I actually wanted to say something that it's, I encourage you to ask questions in science, but you can also ask questions, anything about, her journey, her career, because after all, Vigyan Vidushi program is geared towards the career for young girls. So, and she is sitting right with us as a, our role model. So please feel free to, ask questions. And if you want to, ask yourself, please request us to unmute yourself, and you can ask questions with your camera on also. So this is a request to all of, all the young participants who are attending the talk. Now I'll move on to the second question. And second question is by Debarthi, and she's asking if you could explain the tagline a bit more and how does it happen?
I wish I knew how it happens. That's one of the mysteries. Okay, let me share my slide again. Let me just go to that slide. So the tachocline is the sudden change in rotation rate in the solar interior. It's believed to be caused by concentrated magnetic fields. The hows and whys are still unknown. And to my knowledge, we do not yet have a single numerical simulation, because the people who do numerical simulations of interior rotation with and without magnetic fields to try and understand why the sun looks like the way they do, none of those really reproduce the tachocline's ab initio, meaning out of, from initial conditions. People still have to put in a tachocline by hand. So I'm sorry, but your question is one of the solar mysteries right now. We do not know why the tachocline is formed.
Thanks, Professor Basu. And Debarthi, maybe you can think about working in this field because this remains the unsolved mystery. And you can probably reach out to Professor Basu for more information. The next question is by Jyoti, and she's asking, can aurora discharge be used in a constructive way like a source of energy?
Aurora is actually just electromagnetic waves. So what happens is the solar particles come and excite the nitrogen and oxygen atoms in the nitrogen and oxygen that's present in our atmosphere, and it's the de-excitation that gives you those light waves. So aurora per se, it's just a simple light display. Now, whether we can use the energy of the electrons and other things that are causing the aurora, I honestly don't know. I haven't thought about this, and I'm not sure if anybody is thinking in those terms, whether that energy itself would be enough. Maybe, I don't know. Sorry.
All right, thanks. The next question is by Seema, and she is asking, how early can we know that there are chances to be chances of a solar storm, and since we cannot predict the timely behavior of solar activities?
We get anything up to a 45-minute usually warning, and thanks to things on the instruments on the SOHO spacecraft, because they detect the particles before we do. The instruments on the spacecraft send messages by electromagnetic waves, which doesn't take that long to come. So it's not a huge warning, but nonetheless, it's enough that if you know it's a major storm coming and people are paying attention, that you will be able to take some mitigation effects. The other thing which we monitor the sun continuously is helioseismology actually allows us to do what's known as far-side imaging, meaning figure out whether or not there's a large sunspot on the side of the sun that is not facing us, because the sun rotates, it takes about 27 days on average to rotate. So helioseismology will tell you, oops, there's a huge sunspot on the other side of the sun, which means you start monitoring it when it comes to the near side, and then keep close tabs at it to hopefully see. Like there was one recently, caused all sorts of speculations on the media. Oh, there's going to be a superstorm, etc., etc. The thing is, it's not just that the particles are ejected, which cause a problem. It's the orientation of the magnetic fields of the particles, which also matter. If the orientation of the particles is parallel to the Earth's magnetic field, then remember, parallel magnetic fields repel each other. The storm is not as strong. If, on the other hand, it's anti-parallel, then you have recombination effects and stuff like that, and you could have a lot more energy released and a lot more geomagnetic disturbance.
Thanks, Professor Basu. There are a couple of girls who are asking if they will be able to meet you on site, but I'm sorry to disappoint you. I don't think we will be able to do that this time. At this point, if there are more questions, please either unmute yourself or write in the chat box. You can raise your hand and I will, let you ask questions to Professor Basu directly. Vanna, are there any questions on the YouTube side?
No, I don't see any questions. Yeah.
All right.
Wonderful talk.
Yeah. Are there any more questions?
Hello, good evening, ma'am.
Yes. Can you please show your face on the camera so that we can know who this is, and then please go ahead and ask your question. Yes, Jyoti.
Yeah, good evening, ma'am. So my question is regarding PhD. What would be the better option, like doing PhD from India or from abroad?
Tricky question. There are advantages to both. Now, if you do it abroad, what I found, okay, let me go back to my experience. The disadvantage that I found of doing my PhD in India was that even though TIFR is a reasonably well-known place at that time, not too many people had heard about it. And unfortunately, where you do your PhD, it's the name does matter to a bit. But that is not so much of a problem these days. Also, when I did my PhD, we couldn't really go abroad for conferences. There was no internet. We had to wait for preprints to come, in paper to actually read them. We couldn't post things on archive. It's different these days, but I would suggest that you look, if you want to get an answer to that question, is you take into consideration what field do you want to do your PhD on. Then look at the expertise in India and abroad, and then decide. There are things you can do very well in India. And frankly, India, I don't know what the pandemic did, but at least pre-pandemic, the science funding in India was fantastic compared to what we have here. Also, if you do want to do a PhD abroad, look into different options. Do you want to do it in, say, a place like Germany, where you can get a PhD in 3 to 4 years after your master's, or in the US, where you would still need 6 years because the first 2 years you do coursework. It's a level of preparation question. If you haven't had a large amount of research in your master's, I would say the US is a good place to do your PhD, because you then start doing research. You get a lot of time to learn how to do research, and you get a lot of time. If on the other hand, if you've had research experience, I would suggest a country like Germany or somewhere where you can get it in, a Max Planck Institute or something where you can get a PhD in 3 to 4 years. The one thing to remember, the time to PhD actually doesn't matter. Your academic clock starts when you get your PhD degree. Nobody will look at whether you've taken 6 years or 3 years. It's just a matter of you're 3 years older. That's about it. So I know this doesn't answer your question directly, but the direct answer would be, what field/subfield do you want to do your PhD in? What are the facilities available where in India? Thanks to internet, you know who are the people in those different departments. Research their research productivity. Everybody's publication record is public. Look into that. See what they have done, what the students have done. Conduct your own research.
Okay, thank you so much, ma'am.
So Mantasha is asking, how did you get interested in astrophysics?
Oh, this was, I think I was in the 3rd or 4th standard. 3rd, I think. Maybe 4th. No, 3rd. I had a fantastic science teacher. And she was teaching about the solar system. And that's just about when, the different Soviet and US probes to the solar system planets were beginning to send their images. Now, I grew up in a very small town in Himachal Pradesh. Now, I'm talking about early 70s. We didn't, again, forget internet. We didn't even have televisions. So this teacher was very enterprising. She wrote to the embassies, the US and Soviet embassies, and got all these glossy pictures for us to see. And I was hooked. So I followed more or less a linear trajectory. Astrophysics per se wasn't taught in India in undergrad or MSc, which is, I think, in hindsight, a good thing. You need a strong grounding in physics. You should get a strong grounding in physics. So it's at the PhD level that I really was full-time in astrophysics. But it was a childhood interest which continued.
Thanks, Professor Basu. Samiksha is asking, what's the scope of astrophysics and solar physics in India?
Quite a bit, because India now has its own telescopes. Solar physics, of course, is the history of solar physics in India goes back more than 100 years. The Kodaikanal Solar Observatory, which is a part of the Indian Institute of Astrophysics, and the Udaipur Solar Observatory, which is a part of PRL in Ahmedabad. So we do have dedicated solar telescopes, but only if you can get into IAA or PRL. So we do have theoretical efforts these days. For example, in ISER Kolkata, I think Dipyendu Nandi's group are doing world-class research, but it's all theoretical.
Thanks. I would like to just add that there are also efforts going on with the radio solar science with some people at NCRA, and there is the field of solar physics is growing, and people are using telescopes in India and all over the world to study the solar sciences and other branches of astrophysics. And Aditya mission is about to be launched. So there are a lot of good things happening. Yes. So, all right. So I guess we have a couple of, we can take maybe one or two more questions if there are questions. Please feel free to write them. Otherwise, okay. There is there's a question that, is it important to have a good programming background for astrophysics?
Absolutely. It doesn't matter whether you're an observer or a theorist. Coding is essential. I would say a couple of things are essential these days. Coding, good knowledge of statistics. Astrophysics is changing. We rarely, look at one object, or if we look at one object like the sun, we have, huge amounts of data. So a lot of the work is statistical. So you need to have a good grounding in statistics. So programming and statistics, mathematics, of course, but that's a given if you're a physics student. And the thing I would like to add to it is you need to learn how to write well, because as a scientist, you'd be writing more than you ever imagined you would write, whether it be proposals or papers describing your work. And if you're not a good writer, it doesn't matter how good your work is, people are not going to look at it. And you need to learn how to give good talks. Unfortunately, it's almost impossible to get a job these days unless you can really talk well about your field. You have to be able to make people excited about your field. So I would say coding, statistics, writing, and speaking.
All right, thanks. I think these are really very useful advice. So following, so there's one more question is, okay, which programming language is efficient for astrophysics field?
Okay, there are two answers. If you're going to do observational astrophysics or even simple analysis, you have to learn Python. That's the language du jour. Everybody's using that, and you need to learn that. If on the other hand, you want to continue and do, simulations, then you need to learn C. Learn both. Fortran, there's some fields you still use Fortran because we have legacy software. I still use Fortran because there's a lot of legacy software, but the simulation software is generally written in C. But a lot of the analysis software is in Python, which call Fortran. So if any of you have heard of the SciPy package, SciPy is actually Fortran. You can actually go to the SciPy pages and get the Fortran code. So it's just a wrap around Fortran codes to work on Python.
All right. I think we have had a very good talk and very good question answer sessions. And I think all of you agree that it was an afternoon very well spent. And for that to happen, I would really like to thank Professor Sarbani Basu for giving such an interesting talk. And I'm sure so many students and so many young participants are now energized and to do something in this field. And I would like to clap on behalf of everyone and give the let Vanna say the final remarks, concluding remarks.
Thank you very
much, Sarbani, for a very interesting and motivating talk. And I'm sure the students have thoroughly enjoyed it, and we could see them interact with you. So it was really nice. And you also gave a good feeling that what sun being the closest star and so much yet we have to learn about it. And I'm sure some of them will be motivated to do pursue career in the solar physics. Thank you, Poonam, for conducting the lecture so nicely. And thanks to all the